I'm Bernhard von Stengel from Mathematics, and I will talk about my research topic, PPAD, the polynomial parity argument with direction, or pretty pictures and diagrams. The parity argument is used for the computation of an equilibrium in an economic model, for example to balance out the supply and demand of many goods. Parity means that the endpoints of a path that does not branch come in pairs. If you're a knight in search of a princess and there's only one way to follow, no matter how long, then you will find her. The path is a sequence of computation steps, and here is how it is typically defined. Consider a castle with many rooms, and each room has two doors, except for one room which has the princess in it, and then there's an external door which is the only entrance to the castle, where the knight tries to enter and find the princess. So how does he find her? Well, he enters the first room, and if it doesn't contain the princess, there must be a second door. So that is the door that he follows for the next room, and so on. So he follows a sequence of unique steps. He has no chance to branch, and he keeps going, and eventually he will find the princess. Now we apply the very same idea in a more abstract setting, which I will now describe. Consider a triangulated network, which means we have a bunch of nodes here and here and here that are connected by lines, and these lines form triangles. And moreover, we have the special feature that there is a partition into triangles, meaning here the blue triangles that cover all the nodes exactly once. So each node is contained exactly in one triangle. And the claim is now that there will be a second such partition into triangles. And here's the path following argument, the parity argument that shows this. Consider a designated node W, and now look at the side that is opposite to that node in the triangle, which will now flip over and create what we call a butterfly, namely two triangles that have one node in common. But every other node will be contained in only one triangle, and there is one node that is now not covered at all. Now, because this node has two triangles, we can use the second triangle that we found to flip it over again to create a new butterfly, and then this one will flip the next triangle over, and so on. So we have a unique sequence of flips that eventually has to terminate somewhere, and that is when it finds the node that we started with. So this is the second room partition. So just to see how this connects to our castle, here we have the original partition. We have a unique way to start with by flipping over from this designated node W, and then we keep flipping in a unique manner until we reach the final triangulated partition, which is our princess. Now what is interesting about this is that this path that we have created may be very, very long. So the way to do that is to create a new node, and look at one of the triangles that is created here, into which we copy the existing network, except for the outer node, and we shrink it and put it inside here. So what we then get is 6 additional nodes, 12 triangles, and the 6 nodes will create 2 new triangles, the blue ones here, in a partition which we now follow. And we see that the flipping starts in exactly the same manner as before, and then it enters very soon the little copy that we have created of our original network. Then it leaves that network, and then what happens is that the path of flips will actually be followed backwards. We have no alternative but to follow it, and then eventually we'll have the final steps that create the new partition. So what has happened here is that we have added 6 nodes that actually doubled the path length. And then if we do that again in the small part in here and keep repeating this, we each time double the path length and thereby create an exponentially long path. Now, the research questions associated with path following are the following. This is a method that is often used to compute an economic equilibrium, and they can be defined in abstract ways, for example with these triangle partitions, but they can be very, very long. For example, in a triangle network with 300 nodes, it takes more than a quadrillion many steps to find the other partition. No princess will wait that long. So what we have to do is we have to study alternative methods for equilibrium computation. I conclude with a pretty picture of all the triangles that we have visited.